Today we study chapter 18, Relativistic Formulation of Electromagnetism. As the first step, we study exercise 18.1, which derives Maxwell's equation, differential form of the Maxwell's equations in MKSA units and Heaviside Lorentz unit. For further analysis that unifies electric field and the magnetic field as an electromagnetic theory, as a single theory, we had better use a Heaviside Lorentz unit in which electric field and magnetic field has the same dimension and the structure is very similar with each other. I think I don't have to explain in detail regarding MKSA system, which you are already familiar with. But Heaviside Lorentz unit is the unit system that is frequently used in particle theory. In order to derive the Maxwell's equations, we have to summarize the physics laws regarding electromagnetism. First one is a Coulombs law, second one is Ampere's law, third one is a Faraday's law of induction, and the fourth is the fact that there is no magnetic monopole. Let us begin with the Coulombs law. Coulombs law is the electrostatic force formula between the two charged particles in space. And Q1 and Q2 are the charges of those particles, and R is the distance between the two particles. And the electrostatic force is expressed as 1 over R squared, and direction is along the vector that connects the two particles. So this law satisfies the inverse square law. And over a factor for this interaction is the product of the two charges Q1 and Q2, and it is inversely proportional to the R squared. And over a factor is 1 over 4 pi epsilon 0, where epsilon 0 is the electric permittivity constant in the vacuum. In our analysis today, we just consider, for simplicity, we just consider the vacuum only. Electric field E can be defined with respect to the charge that is placed at the origin, and electric field is proportional to the charge at the origin and proportional to the R squared, and that is a vector proportional to the electrostatic force. Again, the over factor is 1 over 4 pi epsilon 0. This is for the MKSA system, and in the case of a Heaviside Lorentz unit, we do not have epsilon 0 in the denominator. That greatly simplifies and symmetrizes the electric field relation and the magnetic field relation. If we integrate both sides over the closed surface, then we find the Gauss law. And Gauss law reads, electric field integrate over a closed surface, that is a boundary of a volume V, then the answer is just proportional to the charge enclosed by that volume V divided by the epsilon 0. If we use the Heaviside Lorentz unit, we do not have such factor, and it is just charge Q itself. Let us apply the mathematical theorem that is called the divergence theorem. A vector field integrate over the surface as a scalar product between the surface element and that field inside the volume V. This is the boundary of the volume, the closed surface. The circle means this closed surface. Then the value is exactly the same as the divergence of that vector field integrated over the whole volume inside. Okay, if we apply this method to the left-hand side, then the electric field integral is replaced by the divergence of the electric field integrate over the volume. Now the surface is replaced by this volume inside the surface S. And the electric charge Q can be expressed as an integral, volume integral, weighted by the volume charge density. Because this divergence theorem is general, we can choose this volume to be a very small size. Then this argument of both sides must be the same. That means the integrands are exactly the same in every place. So divergence E is rho for the Heaviside Lorentz unit, and in the case of a MKSA system, then it becomes rho over epsilon 0. Let us go ahead with the Ampere's law. Ampere's law is to describe the strength of the magnetic field B, and line integral of the magnetic field B over a closed circuit is the same as is proportional to the current that is passing through the circuit. Sorry. And there is over a factor in the MKSA system, that is magnetic permeability in the vacuum. In the case of a Heaviside Lorentz unit, this is c, speed of light, I over speed of light. There is no mu 0 here. If we extend this Ampere's law to include the displacement current, that is effective current, not a current, but an effective current due to the change of the electric field, it generates a magnetic field too. So that is called Ampere-Maxwell's law. And Ampere-Maxwell's law reads exactly the same as the form, except that current I is replaced by current I plus displacement current ID. For the MKSA system, we have mu 0, and for the Heaviside Lorentz unit, we have 1 over c as over a factor. The displacement current ID is expressed as defined to be epsilon 0 and the time derivative of the electric field flux that is passing through the circuit. This is not a closed surface. Epsilon 0 appears here for the MKSA, and the Heaviside Lorentz unit, there is no epsilon 0. Let us make use of a Stokes theorem, that is for the line integral along a closed circuit that surrounds the surface, open surface S. And that is the co of B integrated over the surface, that open surface. If we apply this one to the left-hand side, the Ampere-Maxwell's law reads co B equals, in the case of MKSA system, mu 0, J, what is J? Here I have current I. Current I can be expressed as a current density multiplied by the surface element. And displacement current is expressed like that. Okay? So, again, with the same method, we shrink the surface S to become a very small area near a point. And at each point, this Stokes theorem must satisfy. Therefore, the left-hand side, this integrand and this integrand, including over factor, must be the same everywhere. So in the MKSA system, differential version of the Ampere-Maxwell's law is curl B equals mu 0 J plus 1 over C squared. Here, 1 over C squared is a product of epsilon 0 and mu 0, and time derivative of the electric field. In the Heaviside Lorentz unit, it becomes 1 over C current density plus electric field partial time derivative. As the third one, we have Faraday's law of induction. If we change the magnetic field with respect to time, then there is an electric field generated around the circuit. So let us consider a surface, open surface. On the surface there is a magnetic field flux, and if there is non-zero time derivative of the magnetic field flux, the electric field is generated. So if you turn around and then come back to the same place, potential difference appears. This is for the MKSA system, and this is for heavy-side Lorentz unit system. Okay. I told you electric field and magnetic field are of the same dimensions in the heavy-side Lorentz unit. Let's see, the electric field and magnetic field, they are of the same dimension, and this is length dimension, and this is area. So this right-hand side has one more length dimension, so we have to divide it by a length dimension. That is, speed of light times dt. This one has a length dimension. So area divided by length. So this is magnetic field times length. This is electric field times length. So in heavy-side Lorentz unit, E and B are of the same dimensions. So both sides have the same dimensions. In this case too, this is a line integral along a closed circuit. So we can apply the same method that is used for the Ampere-Maxwell's law. So if you apply the Stokes theorem, you will find that the col E is minus time derivative of the magnetic field in the MKSA system, and in the case of heavy-side Lorentz unit, you have 1/c. Okay, if we compare the both sides, electric field, magnetic field of the same dimension, this is 1/distance and this is 1/distance. So both sides have the same dimension in the heavy-side Lorentz unit. The fourth one is that there is no magnetic monopole. Okay, this is the Gauss theorem for the magnetic version of the Gauss theorem, and we just replace this electric field by magnetic field, and this integral is the charge inside the volume enclosed by the closed surface. But for the case of magnetic field, this is always zero. Therefore, divergence B is exactly zero in any case. So there is no need to multiply additional factor in two cases. So we do have the unique equation for the magnetic field in both cases. So in summary, in MKSA system, Gauss law is expressed as a divergence E equals charge density divided by epsilon zero. In heavy-side Lorentz unit, we do not have epsilon zero. It is just divergence E is charge density. Next one. Ampere-Maxwell's law is expressed as a curl B is the mu zero times current density plus 1/c squared and time derivative of the electric field. That is more simply expressed. This simple expression appears in the heavy-side Lorentz unit. Okay. And the Faraday's law reads just the curl of electric field is minus time derivative of the magnetic field in the MKS system. And in the case of the heavy-side Lorentz unit, we have time derivative, but we multiply speed of light c to make the dimension of this spatial derivative and time derivative the same. The last equation for the magnetic monopole, no non-existence of the magnetic monopole, is the same in any case. That's it for the exercise 18.1.